Hello everyone, welcome to lesson 9-7, independent and dependent events. In this lesson, we will continue to answer the question, how can you predict the outcome of future events? And our vocabulary today will be independent events and dependent events. Let's start by identifying what an independent event is. So here we have, when one event does not affect the outcome of other events, the events are independent events. So they are not related, they do not change the outcome of other events. For example, if you toss a coin twice, the first toss has no effect on the second toss. Complete the graphic organizer below. So here we have a wheel and a number cube, right? Event 1 and event 2. List an example, so independent events, and describe it. List an example. Using an umbrella. Just because you use an umbrella does not mean it's going to rain. It's an independent. I can use an umbrella for any reason. I can use an umbrella to shade me, but just because I use one does not necessarily mean it's going to rain. So this would be an independent variable, but it would raining itself, if it were raining, then I would use an umbrella. Describe it. So simply using an umbrella does not mean it will rain. Independent is a common word in the English language. Use a dictionary to look up its definition. Explain how the dictionary definition can help you remember the mathematical definition of independent. So when I look at the dictionary, I read that independent means not influenced by others or not subject to another's authority. So what they're saying is that you're not influenced or changed by exterior motives or exterior intentions or other people's actions or opinions, meaning you are independent. The same thing happens in math. In math, when we use the term independent, it means the outcome is not affected by external behaviors or external actions. Or in math, we could use the word variable by other variables. So here is the key point of the lesson, probability of independent events. The probability of two independent events can be found by multiplying the probability of the first event by the probability of the second event. So probability of A and B is probability times A times probability times B. A being the first event and B being the second event. When determining probabilities of independent events, you can use organized lists, tables, tree diagrams, or multiplication to find the probability of compound events. Here we have, for example, example 1. One letter tile is selected and the spinner is spun. So we have these letter tiles and we have a spinner. What is the probability that both will be a vowel? So over here we have two vowels and over here we have one vowel, right? So what do? To visualize it, we can make a tree diagram where we have the tile G, B, E, A. G, B, E, A. And for each one of these, when I get this letter, I have the probability of getting any of these three letters. So I can get the combination of G, A, B, or C, E, B, A, B, or C, E, A, B, or C, A, B, or C, correct? So my sample space would be GA, GA. These are all the probable outcomes. And we've learned this already, where you use the fundamental counting principle and you multiply the first times the second. So here we have 4 times 3 equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 4 times 3 is 12. And now that we have this, the question was, what is the probability of getting only vowels, right? So we look here, which one has only vowels, and when we go down, we see EA, 1, 2, right? I see 2, EA and AA. So there are 12 outcomes, correct? 2 outcomes contain only vowels. The probability that both will be a vowel is 2 to 12, or 1/6 when simplified. We could also use a different method where we multiply the probabilities of each event. For example, probability of selecting a vowel. For the first one, we have 2 out of 4, correct? Here's 2 vowels out of 4. 2 out of the whole 4. Or a half, we could say. Half the time when we use the tiles, we will get a vowel, correct? And for the spinner, probability of spinning a vowel is 1 in 3. Here's a vowel, and the other 2 are consonants, so 1 out of 3. So what we really have is half, right, times a third, which equals 1/6. So using either method of probability is 1/6. Example 2. The spinner and number cube shown are used in the game. So we have our spinner and our number cube. What is the probability of a player not spinning blue? So right here, not blue, but you can spin any of the other colors. And then rolling a 3 or a 4. Okay, so a 3 or a 4. You are asked to find the probability of the spinner not landing on blue and rolling a 3 or a 4 on a number cube. The events are independent because spinning the spinner does not affect the outcome of rolling a number cube. First, find the probability of each event. So, probability of not blue, it's 4 out of 5, right? You can land on a yellow, green, red, or purple. Those are 4 out of 5. Chances are you're going to not roll a blue. And then we have here probability of rolling a 3 or 4. Well, those are 2 numbers out of the 6 numbers. If you simplify that, it's 1/3. So now we have 4/5 times 1/3. So you can see here probability of not rolling a blue and the probability of rolling a 3 or a 4 are here. Not rolling a blue is 4 out of 5 and 1/3 for getting 2 numbers out of the 6 numbers, right? When you multiply those straight across, 4 times 1 is 4 and 5 times 3 is 15. Okay, the probability is 4 out of 15. You can check and make an organized list, table, or tree diagram to show the sample space. Okay, let's try it now that we've done a couple of examples. Here's the question. A game requires players to roll 2 number cubes to move the game pieces. The faces of the cubes are labeled 1 through 6, so they're a pair of dice. What is the probability of rolling a 2 or 4 on the first number cube and then rolling a 5 on the second cube? So we have 2 or 4, so those are 2 numbers, right? So the probability for the first one is we have 2 numbers out of 6, correct? Out of the number cube, which is in turn 1/3, right? Actually, I can just put an equal sign here instead of a comma. It's 1/3. And then the probability of rolling a 5 on the second, rolling a 5, there's only 1 5 in a number cube, so that's 1 out of 6, right? Oops, 1 out of 6. That means now we have to multiply our 2 probabilities. So we have 1/3, or probability of 1/3, right? Probability is 1/3 times 1/6, which would equal 1/18. 1/18. And there we have it. So the probability of rolling a 2 or a 4, a number cube, and then rolling a 5 it's probably 1 in 18 chances. So we've just looked at independent events. Let's look at the probability of dependent events. What is a dependent event? If 2 events, such as A and B, are dependent, then the probability of both events occurring is the product of the probability of A and the probability of B after A occurs. What they're saying is that we first have to solve for A, correct, the probability, and then it's the probability of B occurring after A, what we're trying to identify. So for example, probability of A and B is probability of A times probability of B following A. If the outcome of one event affects the outcome of another event, the events are called dependent events. For example, you have a bag with blue and green marbles. You pick one marble. You do not put it back, and you pick another marble. Right? What we're saying here is because you in the first event you picked a marble, let's say you picked the blue marble, the only other marble you're going to have left in the bag is the green marble. Because you do not put the blue marble back, the second event will be definitely a green marble. Okay, and finally we have example 3, our last example for this video. There are 4 oranges, 7 bananas, and 5 apples in a fruit basket. Ignacio selects a piece of fruit at random, and then Terence selects a piece of fruit at random. Find the probability that 2 apples are chosen. Okay, so 2 apples. Since the first piece of fruit is not replaced, the first event affects the second event. So these are dependent, right? These are dependent events. So let's look for the probability. First piece is an apple. What's the probability? Well, let's see. In total, we have how many fruits? We have 16 fruits. You see? 4 plus 7 is 11 plus 5 is 16. So we have 16 fruits. The chances of getting an apple, because there's only 5 apples out of 16, is 5 out of 16, right? But then he chooses 1 apple. The apple is gone. Now for the second event, there's only 4 apples left, right? 4 out of 15 fruits. Remember, we lose 1 in each one, right? Because we lost an apple. Out of here, we lost the apple, and out of here, the total number of apples, the total number of fruits. So what do we have now? Now we have to actually multiply the 2. We have we can cross-reference, right? When you multiply, you cross-reference and you see that over here these are multiples of 5, so 1, 5, and 3, 5. And over here multiples of 4, 4. Okay, so we multiply straight across and we have 1, 12. The probability that 2 apples are chosen is 1 in 12. Okay, and now let's have our final practice for this video, where we have the probability of choosing 2 bananas out of all the fruits, or the probability of choosing an orange and a banana. First, let's do the probability of choosing 2 bananas. Now we see that we have 7 bananas. So for the first one, right, 7 bananas out of 16 fruits, correct? So for the first one, we have 7 bananas out of 16. This is event 1. But then for the second one, right, we're not going to have 7 bananas, because if we picked one now, we're only going to have 16 and a total of 15 fruits left. Correct. I can try to cross-reference, and I see here that I have, this is divisible by 2, and I have 3 there, and this one 8. So how many 2's do I have at the top? Here I have 3 of them, and here I have 8. So I go right ahead and multiply across, and I have now 21 over, we have 60. Am I right here? 8 times, no, sorry, not 60. 120. Okay. 120. 21 over 120. So you have 21. Probability of choosing bananas are 21 over 120. Could that be simplified? It could be. They're both divisible by 3. So we have 7 here. And in the bottom we have 40. There we go. And for question C, we have the probability of choosing an orange and then an apple. We have 4 oranges and 5 apples. So let's remember that. 4 oranges. So for oranges, we have 4 oranges out of 16 fruit, which is really 1/4, right? 1 out of 4. And if I choose that fruit, that means I'm only going to have 15 fruits left. So it's 15 fruits out of 5 apples that I have. It doesn't affect the apples. And when I multiply across, okay, I multiply directly across. There's no cross-referencing that, by the way. I have 5, and then I have 60. Okay, 4 times 50 is 60. And this can be simplified to 1 over 12. Therefore, the probability of choosing first an orange and then an apple is going to be 1 in 12. And lastly, here we have the guided practice for the warm-up in next class. Take a look through it and make sure that you feel confident doing it. If not, remember, if you're confused by any of the questions, go back to the examples in the video. See you in class, everyone.